later denying sending the money. Suppose that Bob sends, for example, 10 Bitcoin to Alice. What if tomorrow Bob denies this spending money? How the system can prevent Bob from this? This is one of the questions that we should answer in the transaction verification. Another thing, remember, all the cryptocurrencies have a peer-to-peer network. It means that this is a node. Suppose that here is my computer, okay? I have some peers, for example, 3 peers. These peers also have some others. And this is the, for example, Bitcoin network or another cryptocurrency. I don't know, it's not important. This is a peer-to-peer network. Okay? So, if here is Bob creates this transaction. Bob creates this transaction and send it to its neighbors. Neighbors check the transaction, and if they found it is sound, they send to other nodes, and finally miners will receive the transactions, okay, to put the transaction inside the blocks. Now, one question here. Suppose here is Eve, okay? Bob creates a transaction and tries to send the transaction to Alice. So Bob must put some information into the transaction. So if each transaction has some information like recipient address, sender address, sender address, recipient address, sender address, amount, and fee. Also some other information, but for simplicity, for now, let's ignore them. Okay, each transaction has some information like recipient address, the wallet address of the person that we want to send the money to, him or her. In this case, Bob has the Alice's address, okay, and must put this address into the transaction. And also Bob must put his address, sender address, and amount. What is amount? In this transaction, 10 is amount. In fact, it's the value that Bob wants to send to the Alice. Another thing, fee. What is fee? Fee is the money that we should pay to the miners to put our transaction inside a block. For this case, say 1, for example. It's a very little amount of money. And now, suppose that Bob creates such a transaction. Bob, suppose that puts the Alice's address here, puts himself address here, put the amount and the fee here, and send this transaction through the network. And now suppose Bob is one of the intermediate node. Suppose that Eve is one of the intermediate node. node in the network, when Eve receives these transactions, what if she changes the recipient address with herself? And again, send it through other neighbors. How the network must prevent Eve from tampering the transaction? Can you answer me? Suppose that this is one of the questions in your examination. Bob creates a transaction like this, sends it through the network, and Eve wants to tamper the transaction. For example, wants to change the recipient address because she wants to receive the money. She wants to store the money. Okay? How the network prevents Eve from tampering the transaction? You know how? In the previous slides, Zimmer was trying to answer such questions. Let me explain the problem through some codes, okay, Python codes. But before going through the Python codes, let me to recall something. If you remember, I in the previous lectures I discussed the notion of digital signature. Digital signature. And I said using and I gave you the associated codes in Python. If you remember, using private key method sign, putting some data here. In fact, as I said, signature is encrypting some data using the private key. But it's not encryption because all other persons have the public key since they have the public key, so they can decrypt the message. So it's not decryption, but it's authentication. Okay, it's authentication. Now let's back to that's the digital signature. Remember, in the previous lecture I talked about digital signatures using private key, sign a data, we will have a hash. Okay, then using the public key associated with this private key, pub key, verify, method verify, we can check that, let's call it signature, sig. We can verify sig and data both are the same. And in fact, this verification prevents someone to tamper the data. And let's back to the question. How we can prevent others like Eve from tampering our transaction? The answer is using digital signatures. Now let me show you some examples in the code. Critical curve is used. Okay, this common curve variable private key. If I want to print key, I can use this command, serializing the private key and out. Okay. To generate the public key, I use this command. Alice was the private key. Now private key dot public key will return the public key. So please note, to generate the public key, I use this command. Everybody in the network, please note, everybody in network must have a private key and must have a public key. Everybody will keep secure the private key. So only Alice knows her private key, no others. Okay? The private key is secret. So everybody keep it safe. But public key is not so critical. It can be used, but it's not used directly. In fact, an algorithm like SHA-256 or SHA-1, we hash, and the hashed value will be our addresses. For example, let me just a second, please. This is this function calculates SHA-1 hash, takes a public key, and using this command, also previously I sent this program to you about hashing functions. Remember? You have this part of code. Using this part of code, we calculate the hash of the public key using SHA-1 algorithm. If I run the program, let me print public key, yes. But hex. It must be byte-like. Byte-like? What? Who is Alice? ADDR is equal to data must be which data? Which data? Check bytes. It's public key. This is the public key. It's public key. No. Sorry. Public key. Alice public key. Yes, that's right. Okay, hex Alice. Data must byte which data. This other. This area calculate just why we see this error. Just a second, I'm trying to fix the bug. Okay, calculate SHA-1 hash. Calculate calculate SHA-1 hash steps under public key to calculate. No problem. So public key, Alice public key. Byte. Okay, so okay. So I must convert it to byte. It's byte calculation. Calculate SHA-1 hash. SHA-1 public key. It's by public key. They just public key. Check bytes name value. Check bytes like name value. Bytes like print family code public key. Alice public key. Serialization. This error says that I must change the type of public key, but I think it's okay. Let's me to check. Sorry, just a second. Security transaction ID, transaction verify, load key, save key. Alice user Alice transaction verify. No, here I don't have the SHA-1. Transaction ID, signature ready, transaction, decrement, public key, no. Mine address from byte from hex. Let me try this command. Bytes from hex. Okay. Here. Public key. This is the public key. Print public key, public bytes. Key PEN. bytes that from hex. PM as private bytes, Alice private bytes. Private key dr.hex. Private key, load private key, Alice address calculate show on private key to public key, private key to public key, private key to public key. We need this part, Alice address, calculate show on hash, private key to public, load private key to public key. I think we need some of these parts. Yes. I'm not sure, but let's try to generate private key, Alice address calculate show on private key to public key, and that's it. So Alice address calculate show one. This is a private key. Okay, calculate show one hash private key to key. Alice address. Okay, everything is okay now. So we have a private key. This private key is generated using elliptical curve. Okay, then this is nothing. This is just to printing out the private key. This is the private key. Okay, and this part just print out the private key. Here I have a public key associated with this private key. Again, here I'm trying to print out the public key, and here this is nothing. Here I have a function that generates the hash of the public key. So this function returns the hash of the public key. And here, the address, for example, the address of Alice, Alice's address, everybody in the network knows the Alice's address. It's calculated using this function. And here you can use hex. Okay, this is the address of Alice. This is the output of this print. This is Alice's address. So please note, everybody in the network has a private key using this command, has a public key using this command, and has an address using this command. Everybody knows others' addresses. So this address, everybody knows. For example, I know what's the address of Bob. I know what's the address of Alice. I know what's the address of Eve, and everybody knows others' addresses. For example, if you want to send some money in Iraq, you should know his account address. Yes? So everybody, to return what? Naima, you ask, is it possible to what? Or where? I don't understand. What are you meaning? Sorry, I don't understand. What do you mean? Anyway, so everybody has one private key, public key, and address, and everybody knows this address. Okay. So we have here private key of Alice and her address. Okay. I explained this part. This is a digital signature using the private key, command sign, and data. This is my data. You can generate a digital signature. Okay, you can check that the same with this data. And now, our problem. I'm, for example, Bob. I want to send to Alice some money. Suppose that recipient address, this is the valid address of, for example, Alice, or everybody, I don't know, who cares. This is the recipient address. This is the sender address. Okay, this is the sender address. For example, if I'm trying to send the money to someone, this is my address. This is the signature. What is the signature? If I want Eve, if I want to prevent Eve to don't tamper the transaction, the solution is using digital signature. Consider this function, calculate signature hash. In that transaction, I hash these information: recipient hash, amount, fee, and the nouns. What is nouns? I will explain it later. Okay, so simply I put the recipient hash, I put the recipient address. In fact, it must be recipient address. I put the recipient address into the hash. I put the amount to the hash. I put the fee to the hash and nouns to the hash, and I generate it. For example, I call the function here. Okay, now D is the hash of the data in the transaction. Okay, now here Alice signed the transaction. How? Sign D. So this sign.hex, if I run this, this is the signature. Okay, so here in this transaction, this part come from this part, come from here. What's the benefit? The benefit is that suppose that if receive this transaction. So if I want to back to my example, as I said, suppose Bob wants to send 10 cryptocurrency to Alice, or I don't know, Alice wants to send to Bob, who cares? Okay. Bob creates a transaction, Alice creates a transaction, so its transaction has some information. What's the information? Recipient address, sender address, amount, fee. Okay, and now Alice generates the signature using these fields: recipient address, amount, fee, and a number which is called nonce, number which is used once. For the first time it's 1, for the next time it will be 2, then it will be 3, and like. What's the benefit of this nonce? N-O-N-C-1. I will explain it later. So Alice generates a signature and put it beside the transaction and send these transactions to its neighbors. As I said, the network is peer-to-peer, so Alice sends it through its neighbors. Okay, and now if Eve here want to change, for example, the recipient address with her address, let's see what will happen. Oh, sorry, I forgot to record the meeting. Okay. Now, suppose that this is the transaction of the Alice. This is the recipient address. This is the sender address. This is the signature. How Alice calculates the signature? Using here, I have a function that at first creates the hash of these fields: recipient address, amount. It is recipient address. Amount, fee, and nonce. Then here, using this command, suppose that this is the recipient address. I have copied it from here. This is the transaction. Okay, this is the transaction that Alice wants to send to Bob. In fact, Alice wants to propagate these transactions through the peer-to-peer network. As you can see here, this is the recipient hash. So Alice calculates signature hash using recipient hash. Amount is 10. Suppose that the fee is 1 and the nonce is 1. And D is the hash of this data. Now using this command, Alice's private key, alice.sign, Alice creates this signature. So sig is the digital this data, and this is the output. Okay, and now I have it here. I have copied it here. Now Alice sends these transactions through its neighbors, its peers. Okay, every peer simply using Alice public key. This is Alice public key. Can verify that everything is okay or not. There is no error, so everything is okay. But what if Eve changed something? For example, if Eve changed this address Suppose that this is Eve address. I just change one address. Now we have a different address, and suppose that this is the Eve address. Other nodes will check, but at first other nodes again calculates D, and now when they receive this transaction, they have this address, so they must change. So they must change this address. Okay? And now if they verify, they see invalid signature. Okay? And this is how others will be prevented from tampering the transaction. You see? This is one of the parts of transaction verification. So suppose that we have a transaction. Each transaction must have this information: recipient address, sender address, amount, fee, nouns, signature, and finally transaction ID. What? Please note, each person who wants to create a transaction creates something like this. And send this through the network to its neighbors. Okay? So others using this signature simply can check that everything is okay. If someone changed the amount, if someone changed the recipient address, checking the signature, everything, checking the signature, every changes, every tampering will be shown. There is another thing here. Every transaction must have a unique identifier. Every transaction must have a unique identifier. What is transaction ID? Transaction identifier or transaction ID is simply calculated using the hash of all the fields in a transaction, calculating the hash of recipient address, sender address, amount, fee, nouns, and the signature. Okay? See here? This is a function, calculate transaction ID. Sender address, all the fields, recipient address, sender public key, amount, fee, nouns, signature. Then here using these commands, add them to the hash. Digest update, sender hash, recipient hash, put everything beside together and generate the hash. So here I can generate a transaction ID. TX ID is equal to, let me call, this is our transaction sender hash. This is the sender hash, but I must convert it using this command, bytes from hex. Okay, so this is the recipient hash. Now sender hash, I must cut this part and replace it with this part. This is the sender address. Okay, I'll put it here. Sender public key, we have the sender public key here. Sender public key, public key. This is the sender public key. Okay, this is the sender public key. Amount is 10, fee is 1, nonce is 1, and signature signature again bytes from hex, but I copy this signature. This is the signature. Bytes dot from hex. Okay. Oops. I just have to sender public key. Data must be byte. Okay, this public key must be converted to a byte object. However, it's not important. Transaction ID is calculated using such a command, okay, using such a function. ID, and it's a unique value for every transaction. So using this ID, you can she has, okay. But let's talk about nonce. What is nonce? What is nonce? In my example, I considered one for nonce. Nonce, suppose Bob wants to send $10 to Alice. Okay. If nonce, so in our transaction we have Bob address, we have Alice address, we have one, we have the signature. Okay. What is financial fee? Nonce is not financial fee. No. Fee. This is fee. Fee is the cost of putting the transaction inside the block. Okay. Suppose Bob wants to send 10 Bitcoin to Alice. Okay. So Bob must create a transaction like this. Bob and the ID. Transaction ID here. Bob address, Alice address, the amount is 10. Fee is 1, signature ID. Okay. Now, suppose that tomorrow again, Bob wants sent another 10 Bitcoin to Alice 2 times. Okay? Suppose that again, tomorrow, Bob wants to send another 10 Bitcoin to Alice. So he must create another transaction. The transaction will be exactly the same as the previous. So other nodes in the network says, oh, you have previously created the transaction, and before miners put the transaction inside the block, and they will reject the new transaction. Understand? This new transaction is exactly as the same as the before. So only so all the intermediate node and the miners will reject the new transaction because they check that and see that previously they have processed such a transaction. Everything is the same: Bob address, Alice address, the amount, the fee, signature, and ID. Please note, ID is the hash of these fields. So everything is the same. So nonce is a number that in each transaction is used only once. So for this transaction, nonce is 1. But for tomorrow transactions, it will be 2. For another transaction, it will be 3. Every transaction which Bob creates will increase the nonce by 1. For the first transaction, it's 1. For the second one, it's 2. For the third time, it's 3. For the fourth, is 4. Okay? So nonce causes that the signature and the ID be a different, so it's a different transaction. So all the nodes, all the miners in the network understand that it's something different. And this is the transaction verification. Nobody can tamper the transaction. And also another question, and I expect you answer me. Suppose that Bob creates a transaction. Okay, suppose that Bob creates a transaction and sends 10 Bitcoin to Alice. Creates the transactions, sends it through the network, and that's it, finished. How the network, this is the question. Let me write. Tell me how the network prevents Bob to deny sending that 10 to Alice. Tell me how the network prevents Bob to deny sending that 10 to Alice. It's important. It's an important question. Here, Bob creates this transaction, sent it through the network. Okay? Maybe Bob wants to cheat, and tomorrow says, oh, that's not me. That was someone else. How other nodes in the network understand that Bob is cheating? See the information inside the transactions, and according to this information inside the transaction, answer me. Which field of this information prevents Bob from cheating? Who can answer? Nobody? Exactly. That digital signature that digital signature prevents Bob from cheating. Remember, how digital signature is created? Private key dot sign. Okay, who has the private key? Only one person, Bob. If we have this signature here, it means that this signature was created using Bob private key. And who has the private key of Bob? The only person is Bob. So this digital signature inside the transaction prevents Bob from cheating, prevents Bob from denying sending the money. Understand? So this digital signature plays an important role inside the cryptocurrencies. In fact, this signature prevents others to tamper the transaction. Also, this signature prevents the sender to deny sending the money, and it's very important. So this digital signature plays an important role, and that's it. And so let me show you another thing. This is the slide. This is the slides about verification. As you can see, I explained it today, but I explained it through the Python code because I want you to better understand the problem. But let's check the slides. Identity problem. How do we know that Alice initiated the transaction? Using its signature, okay? Identity problem. How do we stop Alice from later denying she sent the money? Again, from the signature. This is the answer. Alice signs the whole transaction using a digital signature, as I showed you, okay? Right address problem. Problem, how do we know that Bob received the transaction? It's a simple question because the address, it goes the hash of his public key. Again, I showed you. Every address is the hash of the public key of persons, okay? So since we have the address of the recipient, so we are Bob or the recipient will receive the transaction. Money availability, how Alice has the money. Okay, it depends on the cryptocurrency. In a cryptocurrency like Bitcoin, the network keeps track every unspent transaction for every address. So since the network keeps track the transactions, so the network now everybody has how much money. In another cryptocurrency like Ethereum, every address associated with a balance like real banks, okay? So simply checking the balance of the, for example, Alice, every node can check that Alice has enough money or not. Another question, how do we know that no money is being created by the transaction? Digital signature prevents tampering the information. But double spending must be answered later when we want to discuss the blocks and mining, okay? So we can answer this question now. Later we will answer it. And this is digital signature. All these questions answered using digital signature. How? In fact, the identity problem is solved by digital signatures. Remember, Alice has a public key, PK, and a secret key, a private key, SK, okay? Two functions, I showed you these two functions inside the Python code, signature, signs a transaction using the private key, this is the private key, okay? And returns the signature, a string, okay? As I showed you in the... And another function called verify. Verify takes public key, a transaction. Data string is the signature which creates using this function, okay? So str, this str here, this str is the output of this function, okay? And checks if this transaction signature is the same as this str, so it will be returned, this function will return true, otherwise it will show an error as you saw in the Python code. Okay, so using these two useful functions, everybody can check and can verify many problems of tampering the transaction, denying the transaction, or solved using digital signature. About Bob wants to spend the money. If Bob wants to receive the money, prove that Bob public key, so simply he is owner of the what are the conditions that make Bob the only recipient? It's a good question. Let me answer this question. I write your answer here. Bob has everybody like Bob. I'm talking, you ask about Bob, so I'm trying to answer with Bob, okay? Bob, like everybody, has a private key. It's a secret key, okay? I'm trying to answer you, Nuraddan. Bob has a private key. Since has a private key, he has an associated public key. Okay? And what is the recipient? Recipient address is the hash of that public key. And as you can see, these hash functions generate a unique address. So since Bob has a private key which generates the public key, the only person who can spend the money, who can receive the money, is Bob. Because the only person who can generate this information is Bob, because Bob only has this private key. Understand? If you want to spend this money, you must prove that you are the owner. How you can prove that you are the owner? Your answer is in the next slide. Let me to topic 4 lecture 1. This is your answer. In fact, Alice's luck, when Alice sends the money to Bob, locks the output using this. There's a PK script here. Okay? In the slides, there is enough information about what is PK script or SIG script. Okay? This is PK script. Alice locked the output with this. The person who wants to spend this money must unlock this code. This is an stack-based code. Okay? The only person who can unlock this is Bob, because Bob has the private key associated with the public key here. Okay? This is about the output. This is the Bob input. Okay? And here is trying to answer your question. There is a stack. In the stack, Bob's signature. At the bottom of the stack, we have the Bob's signature. Then we have the Bob's public key. This is the P script which Alice locked the output. Okay. OPDUK means duplicate the element on top of the stack. So that was the initial state of the stack. After running the code, we have another public key here. The second instruction is op hash. This is the address. This is what you are asking. This is the address of Bob. This is the recipient address. This is the Bob address. So we have this here. Then intended address, it will be pushed to the address. This is the address that Alice showed it in the transaction. Equal verify, check that these two addresses must be the same. So here Bob is trying to prove that this is the right address, and finally check the signature, checks that the signature is true, and that's it. Another question you asked that is there a commission in both Bitcoin and Ethereum? Yeah, every cryptocurrency has a commission. Okay, in fee, the commission is called fee. The commission is called fee. No, you are asking, will the commission in Ethereum increase with the increase in the transferred amount? Please note, in Ethereum, the fee is increased with the size of the transaction, not only with the amount. For example, suppose that the size of a transaction is, for example, 100 byte, for example, Another, suppose that is 200 bytes. Certainly, the fee associated with this transaction is greater than this one. Okay, so larger amounts may be causes to larger transactions, but not necessarily, because, for example, if our amount is 15 Ethereum, Ether, okay, and another is 30 Ethereum, both have the same size, okay. In fact, this commission calculated according is calculated according to the size of the transaction. Okay, the bigger transactions must pay more fee. Okay, and that was about the transaction verification. The most important questions was that how the network prevents others to tamper the transactions, how the network prevents the sender to deny the transaction, and how the recipient can claim his or her money. And these was three main questions that must be answered, and I tried to answer these questions. I tried to explain these concepts using Python codes. Now, if you have any question, please let me know. Otherwise, see you later. No more question? Those Python codes, previously I sent those Python codes, and previously in the previous sessions I explained those parts: how to generate private keys, how to generate public keys, how to sign some information, how to verify some signed information. So watching the previous videos, I'm sure will help you if you forget those concepts. Okay, thank you all. See you later. Bye.